All right, so let's be honest here. How many of you guys actually care about Java and Scala? Oh, bigger turnout. All right. Usually it's all Python. Okay, so why ND4J? So why do we need another scientific computing library? There's a lot of them, right? You know, so there's 15 different standards. I'm inventing the 16th. Wait a minute. No. Okay, so why did I do this? So the JVM, unlike awesome Python, is very fragmented. So if you think about it, there's all sorts of libraries. There's JBLAS, there's Breeze, there's Spire, there's Core Matrix, NetLib BLAS. There's all sorts of matrix libraries on the JVM. They all do different things. Some better than others. Like NetLib BLAS, for example, great library. Abstracts away a lot of your common concerns. You know, it works with native and GPU and whatever else. But doesn't have tensors. Breeze has tensors, but not NumPy syntax. You know, so the goal was to provide a common abstraction in DSL for the JVM that works like NumPy. So if you guys actually have to work on a Hadoop and Spark cluster, you know, because like eventually some of you guys might be interested in learning that, then you want the experience to not suck. So my background is I taught a lot of Python students, and I found that as a Java programmer, I liked Python a lot better for specifically scientific computing. It was a pleasure. I also did a lot of MATLAB as well. So I come from this background where it's like, this needs to exist, but it doesn't. But the good languages aren't productionizable, or they aren't part of the production stack. So the general idea here is that you've heard about Hadoop, big data, Spark, Java, Scala. You've heard about the scale and all that other fun stuff. The JVM, most optimized platform out there for that's garbage collected. It's been around for 20 years, and is a killer app for most things. But unfortunately, nobody's ever figured out how to write elegant libraries for it because the language is clunky. I, as a Java programmer, hate the Java language itself. I'm a big advocate for Scala, though. So a lot of the at-scale computing, I think, needs a good library. So what I'm going to cover tonight are a lot of the underlying concepts of scientific libraries. So for those of you who do a lot of MATLAB and Python and R and whatever else, you guys will learn something about the system side of the scientific languages. And then I'll kind of cover a lot of the different components of ND4J, and you can kind of see this as more or less a conceptual abstraction of what does a scientific library look like? What is it made of? And then from there, I'll kind of explain how everything fits together and what do you do with this. And then what I want to do is compare it to MATLAB, NumPy, and all the other associated libraries. So, all right. So first of all, BLAS and ND arrays. What is BLAS? So BLAS stands for Basic Linear Algebra Subprograms. Whenever you hear about quote-unquote fast matrix routines from Andrew Ng's machine learning class, that's BLAS. So BLAS is a set of routines that are highly optimized for linear algebra. So in this case, BLAS is focused on dense matrices, though. So dense is not sparse. Sparse is lots of zeros, right? So BLAS is highly optimized for dense operations. So this includes things like matrix multiplication. This could be the AXP operation. AXP operation is a great example of that. It's an alpha times x plus y. So what do you do with that? You can do addition with that. You can do subtraction. And it's all linear. So again, highly optimized, and it combines common operations that you would normally never think about yourself. You don't want to deal with that stuff. So BLAS deals with linear buffers. So every underlying implementation of every ND array, whether it's MATLAB, NumPy, or any of these other scientific environments, all work off of what's called a linear buffer. A linear buffer is just a list of numbers. Literally, that's all it is. It's a list of numbers. And then ND arrays are built on top of these buffers. And what they do is they index into these buffers via strides. So strides is like, okay, what is the stride how many elements do I need to move in the buffer to get to the next row? You can use this as a baseline. You can use the strides as a baseline to actually build tensors. You can build 60, 6, and 70 arrays, whatever you can get as crazy with it as you want. So, and then the other concept here is then this idea of an axis. So an axis is, if we just think in terms of 2D, rows and columns. Another way to describe this would be, if we had a tensor, let's just say a 3D image. You have 3 channels, red, green, and blue. So if I have a 28 by 28 image, the tensor is actually made up of 3 28 by 28 matrices. Each 28 by 28 matrix represents a particular part of the channel. You have a red matrix, a green matrix, and a blue matrix. So when you're working with images, even in like Photoshop, what you're actually doing is you're doing a lot of signal processing and all sorts of crazy math, and it's actually on tensors. But if you want to get it down to like 2D space, you grayscale it. So it's a great example. Those are all mathematical operations that you can do with all these scientific libraries. So this underpins anything to do with coding and engineering and math is ND arrays and BLAS. So what does this look like exactly? So this is MATLAB. So we have a standard set of conventions, right? You have a variable, and then you say ones. Maybe a random. Maybe you have give me a matrix that's all zeros of shape 2 by 5. So a shape in this case is just with a simple 2D example is rows and columns. You'll notice then that I say sum a and 1. What does that mean? That means along the first axis. In this case in MATLAB, everything's ones based, right? So give me the sum of the elements along the first dimension, or row or column sum. And then give me the answer. So if you add up all the elements row-wise, you get 5 5s, right? So nice and simple. So here's NumPy. So lots of commonalities here. So you'll notice NumPy.ones. So the only difference here is I have to import NumPy. So NumPy is bolted on to Python, basically. So it's been around for a long time, and it's the standard in scientific computing. Whereas you have like Julia, for example. Julia, again, everything's built in. Like default operations like ones, random, rand-n, binomial sampling. A lot of the things that you would do in math are all already built into the language. NumPy is a library that uses BLAS underneath for computing all these matrices and stuff, right? So you'll know. But other than that, it looks really similar though. So you have ones, random, whatever. Julia, same thing. So what could this look like in Java and Scala? So this is a code snippet from ND4J. So this is Scala. So Scala works, in your cluster. So that's kind of the idea. So typically in data science, you do all your exploratory data analysis in Python. Maybe you have pandas. But either way, you're gonna be subsampling that data. Maybe you're building your models of scikit-learn, that kind of stuff, right? I don't want to do that anymore. I don't want to rewrite my algorithms. So being a Java and Scala guy, I was like, well, why shouldn't this exist? Why doesn't this exist already? So I wanted the same syntax from the lineage of NumPy and MATLAB, something that looks respectable, encourages vectorized thinking. So data scientists are always thinking in terms of vectors, vectorization, sum along the first axis, right? It's highly fast. Don't use for loops. Java, they're like, use for loops all the time, right? That's not scalable. And in this case, I wanted something highly optimized for the JVM. So what I did was I said, okay, let me give myself an abstraction that works over every different Java library. Maybe there's another faster Java library that comes out. So the problem with Java is fragmentation. It's a terrible language. It's fast, but it's stodgy, it's old, and everybody has an opinion about how to do something. So what I wanted to do was create a library that I could write my own algorithms against. In this case, I created it for Deep Learning 4J. That's my core creation. So I created it for the sake of Deep Learning 4J though. So ND4J exists as an abstraction over all the different kinds of platforms that you can do computation on. So here's some of the different BLAS implementations. So there's cuBLAS. cuBLAS is raw C. So this is by NVIDIA. So you have their own proprietary CUDA language. You have OpenBLAS. So you're going to see Atlas and LPAC as well. All of those are open source BLAST implementations. There's a lot of them. So the primary website for this is netlib.org, netlib.org. That contains all the reference BLAST implementations. And that also contains by far the best documentation for the overall spec, right? So other than that, there's also NV BLAST. There's CI BLAST. So CI BLAST is by NVIDIA, or AMD, sorry. And it uses something called OpenCL. So OpenCL is a set of standards that every GPU vendor implements. GPUs are highly optimized for scientific computing, right? They have thousands of cores, thousands. So every time you render something on your phone, on your monitor, it's using a GPU. So the problem is GPUs are hard to program against. Like GPU came out, quite a while back now, but it's still clunky. You still have to take data from the CPU, copy it to the GPU. You have to treat the GPU almost like a server, something you connect to on the internet, even though it's on your computer. You upload data to it, you run some computations on your big matrix, and then you still have to get the data back down. So it's almost like you have a network on your local laptop. Why the heck should I have to do that? Anyways, it's hard, it's brittle, and it's error-prone. And the programming model is completely different. So what I also wanted to do with ND4J was get a set of transparent and easily recognizable CUDA kernels that worked under the same abstraction. So I wanted to treat BLAST as what it should be, a standard. I wanted to treat it as, oh, I want to do AXB. I want to do matrix multiply. I don't want to have to think about, well, which should I use? What's the hardware? All I want to do is just use it on my cluster. And then I can just ask what's available. And then in this case, like, the implication here is my machine learning algorithms will deploy on your cluster as well as your phone. So the idea, like why I didn't just write something against MLlib, for example, great library as it is, you can't run MLlib on a phone. The idea was to have a common abstraction that would work on Android or on the phone. So you could run all your models locally with kind of like scikit-learn, but then deploy it to your cluster without rewriting your code. Cross-platform was the overall idea here. So I only showed you Scala code, but Java looks exactly the same. It's just instead of val, you have ND array. You have IND array. Same idea. So why did I write it in Java instead of Scala? I know Clojure exists. I like Scala I personally like Scala. I don't like Lisp. So I chose not to do Clojure myself, but I wanted to give people the option to. So I'm most experienced in Java, so that's kind of what I did. There's my bias though, but I did it also for the reason of interop. All right. Oop. Okay, so the general idea is you have one library that's a domain-specific language. A domain-specific language is just a language you speak. It's just that, and then it's usually a set of rules, right? So ND4J in this case is a DSL for any matrix computing library on the JVM. So there's lots of them. There's Breeze, NetLib again. I wanted one common standard that I could program against that would work transparently on CUDA or on the CPU. So in this case, each library has its own merits, and I don't want to have to think about which one. I don't want to have to think about which one to use. So it's literally just an abstraction layer. You have a backend, and then those backends are composable. And all you have to do, rather than compiling like you do a native code, you only have a jar file. Let me see how much. Cool. All right. So sorry, just making sure I didn't go over time. So core idea: everything in ND4J is composable. These are just the core components of a scientific library. So a data buffer. So if you remember that buffer object I mentioned earlier, it's just a list of numbers. But it's basically, I want an abstraction over that though. I don't want to care about how the data is stored. The data buffer could be distributed. So you could have shards and all those other fancy distributed systems terms, or it could be on your GPU. It could just be a pointer. So in this case, a great example of this is JCUDA. So I actually have a JCUDA data buffer that sits on top of the GPU and allocates memory, frees it, and it's basically a proxy for a handle. And then I don't have to think about C anymore, where it's like size of, the length, and all this other, free, alloc, I don't have to think about that. I can just think of in terms of a buffer that I create and I destroy. Nice and simple. So it abstracts away the idea of memory. Data buffers have a length. That's it. They have a length and a way to get and put elements. Nice and simple. FFTs, so signal processing is one of the most computationally intensive algorithms out there. So in this case, what I want to do is then give myself an abstraction where if there's an FFT, if there's some FFT implementation out there that I want to use, I can. So where does this come in? Primarily in a lot of deep learning applications for me specifically. You know, signal processing is very computationally intensive, very slow. So I wanted to give myself the ability to swap in implementations of FFTs. The same is applicable for convolutions as well. Convolutions typically work on images. So a convolution, for those of you who don't know, is just a way of superimposing two images on each other. That's all they do. It's basically a really fancy multiplication operation. So, but again, really slow. Another thing matrix libraries have are complex numbers. So no one likes dealing with the imaginary world. Well, you know, but everybody, you know, every library has them. So I wanted to give myself an abstraction for complex numbers as well. So this primarily comes up in fast Fourier transforms, a blast wrapper. So blast wrapper is, again, just a way to access whatever blast implementation I have on my class path. So Java and Scala just have this idea of a class path, which is just the current files that are present on, like, what I have access to, more or less. And then for those of you who know Theano, the idea of an op. An op is just an operation, a dot product, sum, element-wise operations. It's all there. It's just an idea of transforming a matrix. There's different kinds of ops, accumulators in GPU land called reducers, right? And then you have element-wise operations where you have an x, y, and an x, a y, and a z. The XP operation is a great example of that, where you have your x, your y, so a times x plus y is equal to z, right? So z is your result. So I wanted to take a lot of these common abstractions and put them all in one place. How much time do I have left? Just be honest with me here. 10 minutes? Okay, cool. All right. So what I wanted to do was I wanted to make every scientific library swappable. I didn't care what it was. So what I wanted to do was create my own abstraction that I could just delegate to, write my algorithms against, but then I could actually mix and match different kinds of backends. So a backend is just a way of doing computation. It could be mixed GPU and CPU. It could be like maybe I want to take the CUDA FFT and the Intel MKL BLAST, whatever. I don't care. The core here is that you want to have scientific primitives, and you want to have an abstraction over all those primitives. So I want to think conceptually, not at the low level. So these are things that engineers typically do themselves. You know, like an engineer is able to implement these things, but I don't want to have to do that though. Like I want to think in terms of primitives. This gives the ability of scientists to just think about, oh, I want to do fast Fourier transform. I want to know it's fast. Oh, this implementation's, now the other thing is, this implementation's too slow. This new cool thing just came out. I want to try it out. Well, implement a backend, and you don't have to rewrite all your code, right? So again, just to reiterate, Numpy, MATLAB, and all these other guys, there is no fragmentation. They are the dominant platform, they have been, and everybody interops, and it just works. This is a problem in the JVM ecosystem. So the JVM ecosystem is very, despite the language being fast and whatever else, it's fragmented. It's terrible to write programs for, especially when you get into 3 and 4D. Again, like 3 and 4D is highly specialized to images and signal processing, but again, like for those of you who want to be the ability to do it, it should be there, even if you only deal with like rows and columns yourself. So the other problem is like a lot of the current matrix libraries. Only think about 2D. That's been most of the problems. Tensors are actually starting to become more common in matrix factorization in a lot of other kinds of applications. Recommenders. So tensors are becoming more and more relevant over time. So the ability to do 3D, and then on top of that, being able to do it in a distributed setting, and then being able to write your code against one standard rather than like 20, helps a lot. You know, because like it makes you more productive as a software engineer. So the other thing I wanted to do was, for once and for all, bring vectorized thinking to the JVM. So the JVM for scientific computing is slow, unless you have some sort of native bindings or JNI and Java native interface. For those of you who don't know, but I don't want it to think about JNI either. Like there's actually plenty of libraries out there for AMD, Intel. Like every chip maker puts out their own BLAST implementation, their own crazy fast math routines, which is awesome. But all they're trying to do is lock you in. They're trying to get you on their system. Like, come over here, we got this really fast stuff. Like, it's great, right? My goal is to say, well, yeah, that's cool, but I'll just implement your standard or whatever, and then I'll just use it in my code, and I don't have to rewrite it. Reduce lock-in. All right. So other than that, for those of you who know ML a little more, most of my stuff is neural networks, so I have to think in terms of objective or loss functions, convex solvers. So gradient descent, for those of you who don't, for those of you who know what that is, I'm not going to explain ML tonight, but if you know what it is, it's there. Adaptive learning rates. So I had to implement 10 different configurations of Atagrad. So I wanted to put all that in one object. It didn't really fit anywhere else, so there it is. And also random number generator. So everybody wants their own custom random number generator. I don't know why, but everybody has their own custom implementation. So in this case, what I wanted the ability to do was implement a random number generator for the GPU as well as the CPU. So if I want to generate random numbers on the GPU, this gives me the ability to do that. If I want to set a seed, I just say get random, set seed. If I want my probability distributions, there's also distributions object. So I can just say ND4J.getDistributions.binomial.normal.uniform. Whatever you want to do, right? The whole idea here is that you'll notice these are all common patterns we see over and over again on every scientific platform. So again, I want to be able to think in terms of those primitives, and I don't want it to think about your specific implementation. So regardless of whether you guys use it or not, I wrote it for myself, and if you get anything else out of this presentation, it's that, oh, this is what a scientific library is made of. These are the components. Not a lot of people distill it down to, these are the components of a scientific library. So again, I just want to reiterate, the ability to run on Windows is something not most deep learning platforms can do. All of them rely on CUDA or some sort of C blob. So I wanted to take advantage of Java's cross-platform nature. So I wanted to be able to deploy it on Windows or on your Android phone or scale it up to a cluster. Java is the only one where you can actually do all three and do it relatively easily. It's not going to work. It's not embedded systems, right? I'm not trying to go there. I'm trying to go to where the users are and where and just have the most coverage. Basic idea there. So in this case, it's a lot like Linux. It scales up to your cluster, and then it can also work on your phone. Oops. All right, that's it. Thank you. I'll take questions if there's any real quick, just 2 minutes. Well, okay, so I supported CUDA 7 within 2 days of it coming out. Breeze still has experimental CUDA support, and they aren't actually trying to implement multi-threaded, easy GPU access. So what I'm trying to do is my customers require insane amounts of scale because they're all hardware makers. So it's all sensor data, real-time video, 30 frames per second, and real streaming, right? So I want the ability to mix Spark streaming and CUDA, and I want that to be fast and low latency. So I want the ability to bring out the potential, and I don't want it to rely on somebody else to do it. So I have extreme requirements relative to the rest of the industry, but in a way, ND4J is kind of my way of reaching out to the rest of the community and being like, this thing's here. I could have Breeze as a backend for an example. Because I think of ND4J as a DSL. I don't think of it as it's not a hardcore matrix library. It's a DSL. Thanks. If you look at my GitHub, probably not. No, it's no, I don't really. No, because each backend is optimized for every platform. So so if you include an Intel MKL, it will run raw x86. If you include CUDA, it will run only on the GPU. Right. Yeah, so I want if you have 20 CUDA boxes, I want you to be able to run Spark on those, right? So I want that to be easy to do and not error prone. So I want integrations to be a first class citizen, as well as there's always going to be some latency. If you're using any garbage collected language whatsoever in existence, anything that's not C basically, maybe Rust some years down the road, you're not gonna do that kind of programming on the JVM. The JVM's still fast enough for most applications, and if it's not fast enough, throw more hardware at it. So I'm targeting a different market than the embedded people. Thanks. Honestly, okay, so to be frank with you, a lot of the DL4J ecosystem is still very early, right? So the API is baked now. I'm pretty happy with the architecture, but at the end of the day, it's still, it's an open source project. I'm writing most of it myself, because not a lot of people write deep learning libraries and this kind of stuff. So honestly, at least bug coverage helps a lot. Pull requests occasionally if you happen to come across something that you weren't doing. I interact with my users all in real time usually. I'm always on Gitter. I'm always on IRC. Because my documentation sucks. I'll be honest with you. I'm aware of that, and so I'm trying to so documentation as well, right? So if you ask me how something works and then you can write up a tutorial, great. But at the end of the day, I'm trying to bootstrap my own interpretation of ML. I'll say this: we're the only commercially backed pure open source deep learning. I'm also writing the O'Reilly book on it called Deep Learning 4J, DL4J, and Beyond. So that'll be due out this summer. So I'm committed to teaching people, and I'm committed to making sure that you can solve problems. So if you can help me pull requests, issues, complain at me that say this sucks. I love actual critical feedback. I'm not gonna yell back at you. I'm not delusional. So if I can learn something from you, awesome. So we have Word2Vec on Spark, which by default means it'll work on CUDA and some of these other things. I also have just a normal multi-threaded implementation. Both of those interop and export very easily. So we're actually compatible with the GenSim implementation. So we have negative sampling. We primarily use hierarchical softmax, but so all that's there. I have experimental Adagrad support in there as well. So a lot of things, it's there. The Word2Vec is slow. The Word2Vec is multi-threaded but slower than I like, which is why I give the ability to import the C vectors as well. But yeah, it's there if you want it. Yep. So by the way, so I'm also going to implement MapReduce based because the problem with so the only other at scale implementation is the MLib version, but it has problems with memory. You go look at the mailing list if you don't believe me. I'm very conscious of that as well. So I'm trying to I do a lot of intensive work with it. So I'm trying to smooth out a lot of the memory issues there as well. All right, thank you.